Hi, welcome to my presentation on strings in R. My name is Josh Panfil. I'm a fellow in the Society of Actuaries in the United States. I live in Chicago, Illinois. Today we'll be going over how strings work, what they are, and different ways we can use them in R. We'll start with the basics, and then at the end of the presentation, we'll go to a more advanced topic. The resources I'll be using today are R for Data Science by Wickham, and I also recommend taking a look at R in a nutshell if that's available to you. But I'll be focusing on mainly R for Data Science. So let's start with the basics. What are strings? If you have any experience with other programming languages, you've probably seen this word before. If not, strings are an ordered set of characters. That is, they are a string of characters. That's where the name comes from. So, for example, the most common one for beginners that you'll see is the classic hello world. In R itself, the language generally doesn't use the word string. Rather, it will reference characters. So for example, if we look at the class that gets returned for hello world, the string, we see that it returns character. Similarly, using type of also returns character. At the bottom here is just a simple visualization of what a string looks like for a computer. Basically, it is just, again, it's a collection of different characters where each character can be thought of as just one cell in that string. Now in R, we have a few different options for how we actually define strings. First, you can use the double quotes. Or second, if you want, you can use the single quotes. Now, generally, I believe R for Data Science recommends using the double quote, but honestly, in my experience, I prefer using the single quote just because you don't have to hit shift when you are typing the quote character. It is important to note, though, that R does not actually see any difference between double and single quoted strings. So for example, if we run the identical command on these double and single quoted characters, it returns true. Another use for the two different types of quotes is they can be used for nesting quotes. So for example, if we want to put a particular word quoted in R, well, then we can use single quotes for that single word, and we can have double quotes for the entire string itself. And again, you can flip those if you want to. Next up are what are known as special characters. So R has a reserved set of these special characters, such as /t, which is the tab, and /n, which is the new line, meaning go down to the next line. What we can do in R Studio, is if we type this command here, we can look and see the special characters. So let's do that. And now we can see in the help, it does give us this list of special characters and a whole bunch of other information that you might need for other things. So again, we'll see the new line option, carriage return, tab, backspace. So there's actually quite a few different ones. Generally, we don't really see most of these except tab and new line. So we can also take a look at what exactly that will print. So let's go to this line here, and we can see if we select this and run it, now at the bottom here, R will output the exact characters that we have in the string. But if we use the write lines function, now we actually see it where it's using these special characters for what their actual meaning is. So in this case, write lines doesn't output /t. It instead actually includes the tab in the output. So now the reason that works is we're using what's called the escape character. So the backslash is also called an escape character. It essentially tells R that the character after the backslash will mean something special. So we've already seen that with the /t, and we can use it for any of the special characters. Now, if we want to actually print a backslash, we have to do 2. So let's see what would happen first. We run that, and as we can see, let's run it through bright lines, we actually just get a backslash. Now, if we tried to remove that and just ran it, we can already see that RStudio is running into issues because now it thinks this is no longer an actual quote. It is the escaped quote. We'll see different ways to how we can use that. So now, let's say we want to include an actual double quote within this. What we can do is backslash, and now we print out a double quote. So keep that in mind when you are using different kinds of strings. Another option that we often run into are Unicode characters. So Unicode is a set standard for characters, and it includes much more than just the normal English alphabet. So for example, this Unicode code right here is actually the Unicode for the Greek letter mu. And when we print that, R recognizes that it's actually the special Unicode character mu. R 4.0 added a new way to deal with what are called raw strings. So raw strings are what we've been dealing with essentially, where we look at the characters themselves and we do not assign the characters any special function, like with the escape character. We'll see what this means right now. So a common issue that we run into when defining file paths on Windows computers is that Windows paths will use the backslash, but then R will think that the slash is the escape character that we're used to. So what happens is if we try to declare this variable path, for example, we see that we get an error saying that /d is an unrecognized escape character. Now, what does that mean? What happened there is because R sees the backslash and then it looks at the next character, as we discussed, and it expects a character that's in the list of special characters. So it's looking through this list, and then when it sees that it's not in the list, it errors out because this is not a command. So R 4.0 added a nice, convenient way to deal with this to make things faster, because in the past, what we would have to do is either add in the backslash or go in and replace things ourselves. And that is just kind of a slow and easy to mess up process. So R 4.0 added in a new way to specify raw strings. First, you have to add a lowercase r in front of the quotes. And then second, you have to wrap the string with brackets. So now when we run that and we print out the variable that we assigned it to, now we see that R has added in that extra slash for us. Now, we don't have to use curly braces if you don't want to. You can use the square braces or even just regular parentheses. Now, in this case, this also makes it really convenient to quote strings within a string. So for example, if we look down at this next example, instead of mixing single quotes and double quotes. Now we could just use whichever ones we want and then wrap it in the raw string indicator. So we do that. In this case, we've even mixed single and double quotes. And now we print it and we see again, R knows how to add the escape characters when necessary. And if we want to write line like we have been, now we see a nice clean string. So that's the basics for how strings are defined and printed in R. And now we'll start to get into some string functions. So base R has a very wide array of string functions that are very useful and powerful, but there's not really much consistency in how they're defined or named. So it can make remembering and using different functions a little messy. So what we're going to do in this presentation is use the string R library from Tidyverse. So if you install the Tidyverse in your R environment, that will include string R. The really nice thing about string R is at first, all the functions start with str and the underscore, and they all use very consistent definitions in their functions. So if we are using RStudio, as I am, it's really, really convenient because all we have to do is type str underscore, and then the autocomplete will show us all the possible string R functions. Makes it very easy to autocomplete any function that you're looking for. So now we'll look at some of the most commonly used string R functions. Let's head over to RStudio as usual. We will load in the library. And now the first one, very common, is getting the length of strings in a vector. So for example, we define our string vector with 3 strings of varying lengths. And then we use the string length function, pass in that vector, and we receive a nice vector out. Again, this is just very convenient and easily defined. There are built-in options for R, which in this case would be the ncar, returns the same thing. But again, it's nice to keep a consistent library to use. Next, the combine strings operation. So that is done using string C. Now there are some different things that we have to consider for the behavior of string C. We bring up the help and take a look at the different parameters. So we have sep and collapse, and we will see how to use those in a minute. So first, let's again print out that string vector we have. And now let's see what happens when we run string C on that vector. In this case, we get the same exact thing back. Now, however, let's run it where we pass it 2 of those vectors. Now, in this case, what it's done is it has gone through each element in both of those vectors and combined them. So string gets combined with string, and in the second one, string, string, and then hello, hello. So it matches them up element-wise and combines them. Now, similarly, if we want, we can specify which ones we want to combine. So in this case, we combine the first element with the second element, and again, we get them combined. Now, the first parameter that we want to look at is sep. So sep is the separator argument. The default is to combine the strings with no character in between, as we've seen in these examples. If we want, we can define sep to be a space. Now we run that same function and it becomes one string, but in this case, now we have the space between them. Collapse does something different. So the way you want to think about collapse is it collapses the string in on itself. So if we run this where we specify collapse to be a dash, Now we get our 3-string vector collapsed into a single string where each string from the vector is now separated by the character we specify in collapse. So these are very simple but very powerful functions. And if you are interested in the base R functions, you can get the similar behavior using sep and collapse, but again, I recommend using string R. Now, let's say what happens if you try to combine 2 vectors where one is not the same length as the other. So what we'll do is we'll define word1, which just be a single word, and now we'll run string C on that. And what it does is it multiplies this to be the same length as the vector that we're matching it to. So it becomes a length 3, and then we get the same behavior as we've seen before. So now what happens is this particular string is combined to each element in string vector. Now, sometimes you might want to combine strings of different lengths. What happens in that case? Well, it still works, but we do get a warning that a longer object length is not a multiple of the shorter object. So 3 is not a multiple of 2, so it still works in the sense that it combines element 1 with element 1, element 2 with element 2, and then element 3 with element 1. So it recycles and starts over at the beginning, and it still gives us a warning letting us know that happened. Now, as you might have seen with different types in R, is that if an NA occurs, that NA generally propagates throughout any functions that we run. So what I mean by that is if we now define the third element in string vector to be NA, and we run string combine, where we want to combine the first string, in this case it was str, with that NA, you might expect it to return strNA, but instead what we get is just the NA special value again. So string R has the string replace NA function, and what that does is it replaces the NA character with an actual string NA. So now when we run that, now it can actually work again, and we get a combined string rather than an NA special character. So you always have to keep that in mind, that R is generally extremely safe with NAs, and rather than assuming you want to cast that NA to a character, it will just return an NA no matter what. So this string replace NA function is nice to be able to get clean output. Sometimes we might run into a null instead of an NA, and now those get handled in their own way with string R functions. So if a string R function sees a null or any kind of object that is length 0, it will just ignore it instead of returning an NA. So for example, well, let's look at what happens when we combine these two strings, or this string rather, with a null. All we get is this first string back. Now, the nice thing with that is, for example, we can use it with if statements to output different results depending on if the if function returns true or false. So now let's say usename is false. So what happens is we just get this nice little hello message back, because it just completely ignores this section. Because if you give R an if that returns false and no else statement, you just get nothing back. So we can, if we want, we can change this to true. And now we get the full message. Next up, a very common function is subsetting. So a subset means that we take out a portion of a string. String R has the string sub function, and we'll take a look at how it works. So in this case, string sub really just has two important options, start and end. And all that means is for each string in the vector, the start indicates which character to start with, and end indicates which character to end with. So in this case, since we're saying start at 1, end at 2, we run it, we get the first two characters from each string in our vector. So as you notice here, the start and end are inclusive. Now there are a few different ways to work with this. So for example, if we try to use string sub and have the end set past the end of the string, it will just output the entire string and it won't return an error. So if we say end at 4 for this 3-character string, we just get the whole string. Another nice capability of this is you can use negative numbers, so you can think of starting from the end of the string. So for example, if we look at hello, the O would be -1, this L is -2, this L -3, and so on. So we can use the string sub function with negative start and negative end. And now what this means is we subset starting at -2. So starting at this L and we go to -3, that returns LL. Same thing with the other ones, we get IN and ST. Now, even though you can visualize it as starting from the end, it still returns them in the order that they actually appear. So in this case, for string, we get IN and not NI. So just keep that in mind. Now, another thing we can do with string sub is actually change the characters in a string rather than just return them. So let's take a look, print our string. Now let's say we want to replace the first two characters in each string with the letter X. Well, what we do is we run string sub on it, set 1 and 2 for start and end, and then we use the assignment operator to actually change those substrings. So let's run that. And now, as we can see, the first two characters in each string are replaced by the letter X. Another very common operation that you'll encounter if you use R in any kind of data analysis is ordering and sorting. So again, we'll run over to RStudio, and these functions may sound like the same thing, but they are very slightly different, and we'll see how. So now let's define a new string vector with apple, eggplant, and banana. And let's see what we get when we run order and then sort. So order returns a vector of numbers, whereas sort returns the original vector, but it's sorted. So what's happening here is that string order is returning the sorted index of each value. So in this case, it looks at the string vector. Apple will be sorted first. Banana would be second. And eggplant is third. So we get 1, 3, 2. String sort, like I said, actually sorts and returns the original values. So if we didn't have string sort, what we could do is use string order to get the indices like we saw, and then wrap that within a call to the vector like this. So in this case, we run that, and we get the exact same output. So one thing to consider is that when you're running sort or order, it's going to treat numbers as strings. Now, what does that mean? So ask yourself, what do you think this numeric vector is going to get sorted as? If we're sorting as numbers, we would expect 1, 2, 10, 40, 100. But now if we actually run this, let's see what we get. We get a vector of characters. So the way this sorting will work is R will look at the first character in each of these, treating it as a string. So the ones come first. So we get 1, 10, 100. Then it looks and sees a 2. So then we get 2 at the end, 2 second to last. And because 4 ranks behind all of these as characters, we get 40 last. So you have to keep that in mind, that if you will be sorting a numeric vector using string sort, you may not get the order you expect. Now you can specify the numeric argument as true, and what we get is the numbers sorted in numeric order, but still they get returned as strings. Now contrast that to using the sort function, which is built into R, that returns the numeric sorting that you would expect. So sometimes you might run into a case where you have a mixed vector. So you have numbers and characters, and you might ask yourself, how will these get sorted? And I've even thrown in the Unicode mu character. So now let's see what happens. We get the numbers first, the words that start with letters come after the numbers, and then we get mu at the end. What we'll see in a minute is that your locale actually determines how things are sorted. So in this case, R treats these numeric characters as lower on the sorting order than letters, and then further Unicode characters come at the end. Now again, we can use the numeric option, and what that does is it sorts just the numerical values in numeric order, and we get the same exact order for non-numeric values. So you have to keep in mind how different kinds of vectors will be sorted when you're using these functions. So my advice there is just to be careful. Now, I had just mentioned that something called a locale will change the behavior. So now let's take a look at what that means. There are a few different ways that you can actually call your locale. So first, we can look at session info, scroll down to the locale setting. We can use sys.getLocale that returns a semicolon separated list. And then finally, string I has a string I locale info. So now what does this mean? Let's take a look at the output. We get language, EN for English. My locale is the US. Now that gives me the English US name. So this means that sorting, capitalizing, any type of function on a letter or number, it will use English United States rules. Now we can actually see how that might be a little different between languages. So, for example, we have this character here, which I'm not even sure what it is because I've never seen it since this is not an English character. And we can look at what happens when we run string to upper. We get 2 capital I's back. However, we can set the locale to Turkey. And now what we get are 2 characters that, again, I do not recognize. That is because now that we're using Turkey rules, the output is going to be different than what I'm used to with English rules. And now something else that I've mentioned here in my comment is that if you look at the book R for data science, you'll see that the output doesn't exactly match what his output does. And I suspect that is because the authors of the book are using a different default locale than I am. So the values come out a little different. So as I mentioned before, this can really become confusing in an instance where you are sorting. So string R has the built-in letters variable. What that does is just lets us play around with something that gives us some examples. So let's run sort on that, but instead of using English, what we're going to do is use Estonian. So now, before we run that, we can look at the bottom here, and as you know, I'm an American. This sorting is what I am used to. But now we use the Estonian sort, and something strange happens for me. We see now that instead of Z being at the end of the alphabet, Z is in fact between S and T. So that is because the alphabetical rules are different between English and Estonian. So it's just something to keep in mind. Now, again, let's look at our string vector, apple, eggplant, and banana. There's even a difference between English and Hawaiian sorting. So in this case, Hawaiian actually gives us eggplant second and banana last. So that is just something that you have to keep in mind if you're going to be working with an international audience like we are here with Statistics Without Borders. In my daily job where I use R, I'm generally only working with American audiences. So it generally doesn't come to mind, but it is something that I would need to consider if we work internationally. Now, if you want further information, you can look up the comparison help page, and it gives us a description for using comparison of strings. And we'll get into how locales affects things. So if you are ever confused about how these different sortings work, you can consult the help and see the different options. We can see that they use the exact example that I did, where Z comes between S and T. And it gives a few different other examples. So just keep that in mind. Okay, let's move on to some exercises for the first section. Number 1 is write a function that turns the vector A, B, C into a string A, B, and C. Number 2 is using X equals the vector I'm showing there, replace the first half of letters in each string with 0. So go ahead and pause here and work on that. And when you're ready, go ahead and press play. Now let's take a look at the solutions. Okay, so let's go to RStudio to make this easier. Number 1, again, is write a function that turns the vector A, B, C into a single string A, B, and C. So first, to set this up, we're going to save that vector into x. We'll also take the length of x, which gives us a 3. Now here's my solution. So we'll run that, and then we'll break it down. So as you can see, we get the expected A, B, and C. Now let's take a look at each component of this solution. So the first part is we are going to look at the vector, but we're going to exclude the final element of the vector. So in this case, we're going to exclude C. Now we use that using the x length that we just calculated, and we use the indexes to get the other elements. So let's see what that looks like. Okay, so A and B, as expected. Now what we'll do is we'll use the string C function along with the collapse parameter set to a comma with a space. We run that, we get A, comma, space, B. So that's the first part. Next up, what we're going to do is look at the second part. We're going to use only the final element in our vector. And we are going to use string C again to combine that with and. So now we have and C. So at this point, we have two separate outputs, A comma B, and then and C. So now what we'll do is we'll use the C function from base R to combine those into a vector with two elements. So the first element is A comma B, second is and C. And now once again, we're back to our actual solution. We're going to use string C with, once again, the comma as the collapse argument, and we run that like we did earlier, and we get A comma B. Then we have our collapse, and then we have the and C. There you go. The second exercise was using this vector, replace the first half of letters in each string with 0. So this is an interesting problem in the sense that each string within the vector is a different length. So you might remember from the presentation earlier that we have this string sub function. But now the question is, since we want to replace a different length string in each element, what do we do? So we're going to use the string length function that we have from string R. Now let's look at that first. We get 3, 3, 5, 4, 1, 16. So immediately you have to ask yourself, what does it mean to replace the first half when the number of characters is odd? So I actually didn't specify it in the question, just to let you guys think it through. And what I chose to do in this case is round up. So for example, now if we divide by 2 to get the first half of each string, we have numbers of decimals, and you can't replace a decimal character. That wouldn't make sense. So I've used the ceiling function. And what that does is it rounds the value up to the nearest integer. So as we saw before, we had a 1.5, it's now a 2. Similarly, 2.5 becomes 3, and so on. Now, next up, we need to figure out what we're actually going to use in string sub. The nice thing with string sub is that the start and end arguments can take in a vector. So the start and end for each element in the string vector does not have to be the same. Now in our case, we do want to start the first character in each string, but the ending character is going to be different. So now in this case, what we want is this string rep function. Now this is from base R. What this does, if we look at the help, we see that we get the times argument. It's an integer vector giving the number of times to repeat the respective elements of X. So now what we can do is use string replace along with the values that we calculated just before. And what this will give us is this. So now we have the correct numbers of zeros for each string. We can use string sub to look at the values we're going to replace. And what we see is that now each one is lined up properly with the number of characters. So we run that entire function now and using the assignment operator. Now we've actually changed X and we can see that the proper number of zeros have replaced the characters in each string. So again, something else to think about with this problem is what if I asked you to do the second half of characters instead? Also, how should the behavior be handled with odd numbers? So for example, use the floor function instead. Now, in that case, for a single character string, that would replace nothing. But these are just different options for us. So those are the kinds of things you need to think about when you are working on functions like this. Okay. That concludes the basics of working with strings in R. Now we're going to get on to a more complicated topic known as regular expressions. Regular expressions are also commonly abbreviated as regex or regexp. They're defined as a sequence of characters that specifies a search pattern in text. So that sounds pretty simple, but as we actually start using it, it's going to look very confusing at first. And honestly, it'll probably be confusing even as you start using it. You shouldn't be discouraged because they are confusing to everyone, and it's very, very easy to forget how they work, so you'll have to look it up again later, unless you're working with strings and regex all the time. Luckily, there are many helpful options to work with regex. So for example, RStudio has a plugin, the Reg Explain, and there is also a website, regexr.com. Now on this, what happens is you can define your regex expression, give it text, it will show the matches, and it will also explain it to you very nicely in the bottom here. String R also has a nice tool that is string view and string view all to help you visualize your regex. Just some general tips as we work on this. You really want to break down any complex regex into a series of simpler expressions, especially when you're thinking about it. Start simple and then build up complexity if you need to. Also, always ask yourself if regex is necessary in the first place. So R for data science, for example, linked to this Stack Overflow post where we look and we see this regex and it's absolutely crazy, difficult to follow. There's this huge diagram, and this was for determining if a email address is valid. So again, just use pre-existing tools if you have them. For example, use the pre-existing tools available in R before you get overly complicated with your regex. Now we're going to move on to how regex actually works. We'll first look at the common characters, and then later on we'll look at common functions in string R. And the next few sections are going to be basically all in RStudio because it's much easier to learn as you do regular expressions rather than just reading off a table. So here are some common characters that we'll see. As you can see, there are many and they look perhaps somewhat strange. But as we've seen some already, we already know the escape character, and we'll see how a lot of these work. Okay, we're going to jump over to R and make sure string R is loaded up. We are going to define a variable X with apple, banana, and pear strings. And now we're first going to look at how this string view function works. So let's run that. And now we see that we get this nice output here in the RStudio viewer. And the AN is copied in banana. So now what's going on here is we've specified that we're searching for AN. If we look at the help, we are specifying the pattern argument. So in this case, it's simple. We're just looking for the characters AN. And since we use string view, it only highlights the first match. We use string view all, it highlights both matches now. Okay, so in this case, we are just looking for the characters AN. Now we can actually start looking at the different characters that are used in regex. So first we will use the period, aka the dot. And now what we do here is the dot is a special character. What it actually says to regex is allow this to be any character that is then followed by an A and then any other character. So this could be XAX, 1A, or 2A, 5, anything like that. As we see from our example strings, BAN match and EAR match. So that's our first special character, the dot. Now, the next question usually is, well, what if I want to match an actual dot? So you might think first that it is just using the escape character, then dot, but let's see what happens there. We get an error. This is because, as usual, R thinks this is a special command /dot, but we want to send /dot to the regex. So we need a second one. Now, if we look at that, we get that without an error. And if we do right lines, now we actually send the string that we want to send. So what this means is look for an actual A dot C. So if we run it on this set of characters, only A dot C matches. So hopefully that somewhat makes sense. If not, that's okay. It's the kind of thing that you'll have to get used to as you use it. So as I mentioned earlier, R 4.0 introduced the raw character indicator using R and then a set of brackets. Now let's see what happens if we use that here. Once again, it considers the dot to be any character that we're searching for, rather than the dot that we want. So in this case, honestly, I think it will be easier to not use the new raw character string indicator, because we're going to see in a minute that the brackets also have their own meaning, and it might just make it easier or harder to read rather. So in this case, we could use a single slash and a dot and use the brackets and the R indicator to successfully get that string that we want, but it might just be harder to read. Now, what if we want to match a single backslash character. How do we do that? So, as usual, you might think just add a backslash to your backslash like this. And again, we get a bad escape sequence. Well, maybe it's 3, but now we can see that R itself is already getting confused. And since I just ran that, it thinks I wanted to make this into an escape character for this whoa, and now everything after it ran. So let's not do that ever again. And what we actually need to do is 4 backslashes. So 2 backslashes become 1. So what we end up sending to regex is 2 backslashes. If we look at this, okay, so now that actually sends the indicator that we want to search for an actual backslash. So let's see what happens. And there we go. And even in this case, we needed to use the double backslash to even send 1 backslash in the string. So as you can see, backslashes can be an absolute mess and very, very annoying to deal with. Next up, we have the anchors. So there is the caret anchor and the $sign anchor. The caret indicates start of string. The $sign indicates end of string. So now let's see how that actually works. So we'll go back to the apple, banana, pear. And now when we say caret A, what we're saying to look for is give us the strings that start with an A. So we run that and we get these results. Only apple is highlighted. Let's use string all just to make sure we're not missing anything. And as you can see, still it's only apple because apple is the only string in this vector that starts with an A. Similarly, the $sign indicates the end of the string. So in this case, we want to highlight the A's that happen at the end of a word. And in this case, only banana works out. Now, let's do this. Let's create a new vector where we have apple pie, apple, and apple cake. And we'll do string view all. And as expected, if we look for apple, we get a match in all 3 strings. Now, let's see what happens when we run string view all, but we specify caret, apple, $sign. What that means is we're looking for an entire string that is apple. So in this case, we only get the middle one because the other 2 are not complete strings with just apple in them. Next up, it is common to want to search for digits in a string. So let's say you want to pull out a string or a digit from a string. Now, again, as usual, we're going to define this. We have a new vector where apple2 and then 3 string are new strings in that vector. And \D is the escape character for digits. And in this case, I just used another example of where it might be possible to use the raw string format. But again, I just don't recommend it. Instead, we'll just use the \D, because as usual, we need to send an actual \D to regex. And if we didn't include this second one, it would try to send a command/D and would get the usual error. So again, it's the kind of thing where it's like you just have to remember the rules and avoid any of these very, very easy to make mistakes. Next up, we have the white space character. So that's \s. And again, we'll use the same string from last time. We'll do view all just to make sure we're not missing anything. And as you can see, when we do \\s, we nail the spaces in the strings. Okay, so as I mentioned before, the brackets actually mean something for a string in regex. Now what it means is we can match anything that's within those brackets. So A, B, or C in this case. Now let's take a look at how that works. So we'll do string assignment to X as usual with this new string. And we will do string view all. And again, it's A, B, or C. So now we run that and we get the A in apple pie, the A in apple, and all the C's in the string. And now this is why I warned against using the brackets. It's because if we run this, now when you see it, you might think, okay, we want to search for any of A, B, or C. But what this is actually doing is searching for the complete string A, B, C. So as you can see, it looks like we're searching for one thing, but we're actually searching for the entire word. So it's just easy to make that mistake and mess up that kind of search. So that's why I do not recommend using the raw string indicator. And in the same way, if we throw a caret in the brackets with the other characters, that is negation. So that will match anything except A, B, or C. So let's do that. And now we get all the other characters. So you do have to keep that in mind, that the caret, if it's outside of these brackets, it means string starting with, but if it's inside the brackets, it means not. Not sure why that was chosen, but that's the way it is. Now, another option that the brackets give us is a different way to use the dot character. So, for example, let's say we want to match a string that is A, then any character, then C. Now we can do that with the \\, pardon me. We want to match the actual dot, not the special character, any character. So we're searching for A.C. And surrounding that with these square brackets tells regex to actually look for that dot rather than using its special meaning as a setting for anything. That means this string, regex string here, is the same as this pattern. So both of these look for A, actual dot, then C, as we can see there. Now we can also combine that with the asterisk to indicate we want to look for a literal character, the asterisk, and then we can use the dot outside of the asterisk to search for anything. So in this case, we see A star B or A star C and B star C both match. Similarly, we can use the brackets with a space inside to search for an actual space. So in this case, we are looking for A and a space. And as we expect, we find that match. Now I copied this note from R for data science because it's very helpful to keep this in mind. So using the brackets will work for most regex meta characters, and they're listed here. For example, a few that we've already seen. And he writes that unfortunately, a few characters have special meaning even inside a character class. Must be handled with backslash escapes. So as you'd expect, the square bracket makes sense. The backslash, caret, and minus. Now, moving on, the next meta character we want to focus on is the OR operator. So the OR in regex is the same OR that we have already seen in R, the vertical pipe. So in this case, let's do blue, red, and green. And now we want to view a match for blue or red. So there we go. This is just a nice, convenient way to reduce the amount of functions you need to call, because you can just put them in one string surrounded by the pipe. And again, if you think back to the string C function, you could use the collapse operator with a pipe character, and that might make it easier in the future when you're using different regex functions. Another cool thing we can do with the OR operator is nest it within parentheses. So the color gray can be spelled two different ways, with either an E or an A. And if we're trying to match either one of those, well, then we can just do E or A within parentheses. And now we can search that, and both of those will be matched. Very convenient. Next up, we will look at the different repetition operators. So to specify repetition in regex searches, we will use the question mark, the plus, and the asterisk. So we're going to use this example from R for data science, and we will use this very long string. Now, let's see what happens when we do string view CC question mark. As we can see, question mark is defined as 0 or 1. So what that means is when we are using this search, the first character has to occur, but then the character before the question mark only has to occur 0 or 1 time. So that's why when we use string view all, we get two matches. First, we get CC, because that is C and then C one time. And now we get a second match of just C. Now you might ask yourself, with this triple C occurring here, will this second match be two C's or one C? Well, we can actually use another function that we'll look at right here, actually, is the string extract all function. Now we run that and we get CC and then just one C. The reason why is because regex searches and matches do not overlap. So once we've already matched these two characters, they are not available for another match. So then the second match can only be this one C. Now we can also use the string count function to see that we get two matches, and we've seen with extract all that it's CC and then C. So to summarize that, the question mark means 0 or 1 times. Now, a convenient way to use this is if you are searching, for example, using websites. Some websites will be defined with only an HTTP. Others will be defined with HTTPS. Now, let's say we wanted to match both of those. So HTTP or HTTPS. We could use the or operator, but it's much easier to just use HTTPS ? Because it makes the last character a match if it occurs 0 or 1 time. So as we can see over here on the right again, we get 2 matches. The second one still matches without the S. Now the plus operator is similar, except it matches 1 or more of the final character. So in this case, let's do string view all. What we're searching for C++. Now what this has done is it goes over here and it searches again, it gets that first C, and now it will match if there's 1 C, 2 C's, 3 C's, and so on. So essentially what this one is actually doing is searching for CC, CCC, CCC, and so on. So we end up matching this entire group of 3 C's. And again, just to take another way to look at that, we can extract all, and we only get that 1 match. Now you can combine these repetition characters with the square brackets. So let's see what happens when we run that. So now a reminder, the plus means 1 or more. And what we get is a match for C, then L, and then X, and we allow X to repeat any amount of times. So if we write that out in another way to look at it, and we can play around with it, let's do C, L, L. And as you can see, it's matching either one of those. So L and X can occur however many times, and we'll still match all of them. So now we can do any kind of combination of those characters, and we keep matching until we get one that is not within that string. So as you can see here, now once we've added a 2, it breaks this match of L's and X's, and we don't get the final XL. Similarly, we'll look at the previous example, except now we're just going to throw a bunch of extra S's. And in the second one, we'll leave it without any S's. And now what we see is that the second HTTP does not match, because plus means 1 or more, so that S has to occur at least once. Now, the star operator means 0 or more. So 0 or 1 or 2 and so on. So again, we'll do string view all on the original X, and using the star operator gives us the match on the 3 C's. Just as another view on this, we'll do similar websites, and now we'll do it with all 3. So we've got our extra S's, our 1 S, and then no S. Before I run this, try to think to yourself, what's going to match for each? So we'll do it with the question mark, which is 0 or 1. So it matches all of them, but it ignores the extra S's. The plus is 1 or more. So it matches the first 2. And the star is 0 or more. So it matches all 3. So these operators are very, very powerful. And you want to keep that in mind if you're doing any kind of searching for repeating characters. Another option that we can use with repetition is handling the different spellings between American and British English. So American English spells color without a U, whereas British English uses the U. So we can throw a question mark into the search after the U. And what that does is it tells the regex we want to search for either of these spellings, whether U is there or not, and it will match both. So again, we see an occurrence where language may differ between countries, but we can have these specific functions to avoid that. Now, another option for repetition is using the curly brackets. We can actually specify the number of repetitions that we want to match. So real quick, let's take a look at the string again, just so we haven't forgotten. And now what we'll do is use C curly brackets 2. Okay. And in this case, we only match where it's repeating twice. I've also included this website here because it includes a nice description and set of examples to make these examples and these users clear. So that is the curly brackets N, and I have these mentioned here at the bottom of the table. And now we can run through and see what happens. Now, if we specify 4 repetitions, now we get no match because it only goes up to 3. In this case, we can do curly brackets N comma, and that searches for N or more. So if we think back to the plus operator, that's 1 or more, that would be the same as doing 1 comma blank and allowing for any match. So in this case, 2 or more C's, we have 3 C's, and there we go. Now, R for data science had the next syntax as you can leave the first part blank for M or fewer. So in this case, we put the M second, meaning up to M. Now, R for data science originally defined it like this, and as you can see in my R installation, it actually errors out. So you do need the 1 there. So now in this case, we're saying up to 2 repetitions. So again, now we're going to match CC and then the other C. Finally, we can do the N comma N syntax, saying between 2 and 3 matches. And now in this case, it still matches the 3 because we set that as our upper limit. I've added a few more examples here. Now, if we look again at our x2 vector, we have those different HTTPS strings, and now we can use the different repetitions. So this saying has to be 2. This one is between 1 and 3, between 2 and 3, and then 4 or more. Now, the syntax 2 comma 3 is a match of 2 or 3 repetitions, and it's going to match the longest string that matches that search. So if we look at the previous example, we could match 2 here, since it's 2 or 3. Now what we can do is use the question mark after our bracketed start and finish, and then that will instead match the shortest string. So now instead of matching the 3 S's here, we're going to match the lowest amount that matches, so 2. Similarly, now let's go back to our previous example where we are searching for CLX, where L and X can repeat as many times as they want. But now let's throw in a question mark at the end there. And what we get is the shortest string that matches. So in this case, CL matches rather than this entire CLXXX. And again, just one more example. Since we're using the brackets around L and X, it's either of those characters have to occur one or more times using the plus symbol. So again, we match the shortest. Hopefully all of this is making a lot of sense for you guys. It can definitely be confusing. It's even sometimes difficult to describe just because it's so easy to get tripped up on my words here. Now, next example, we are going to use the fruit vector. That fruit vector comes from string R. It's a nice way to practice. So string R provides sentences, fruit, and words. So if we use the head function, we can look at the first 6 examples in fruit, and we have apple through bilberry. Now, the next regex we're going to look at is back referencing and capture groups. These are definitely a little hard to explain without a lot of examples. So I recommend using the R for Data Science book and going through their examples there, and then maybe just Googling on your own as well. So now what we're doing here, let's run this on string view and see what we get. So we're saying search for AN, and now we round those in parentheses, which makes it a capture group. And then what we do is we can back reference it using \\1. And what this is essentially saying is search again for whatever matched the first search. So in this case, we match AN. So now essentially what happens is this search string becomes AN, because we're saying look again for the first group that we captured. So that's why we get that there. Now what we can do in that case is use ... to say match any 2 characters and then match them again. Now let's see what we get here. So we can, and we're also using the match equals true argument, because if we didn't, fruit is actually a pretty long vector, and it would just really clog up the output. So by matching true, it only returns the ones that match. So anyway, what this does is it goes to each string and it looks through, grabs any 2 characters, and then if those characters appear again, that's going to become a match. So in this case, for coconut, for example, the first 2 characters are CO. And since the next 2 characters are CO, that counts as a match. And the same for these other ones. And then we get down to salal berries. So in this case, SA would match this first double dot, but then SA does not occur again. So that's not the match. So the next search becomes AL, because that matches double dot. And then AL occurs again, so that matches the 2 groups. So again, we create a capture group here, and then we back reference it, saying, let's get that first capture once more. So those are the various common characters that you'll see, the special characters that actually have a special meaning in regex rather than just searching for whatever their character is. Now the final thing we want to go over is common string R functions. So again, I've just created a simple table here with some of the most common ones that you might use. And then we'll take a quick look at how to use them in our studio. There are, of course, many other string R functions, but these are probably the ones that you will see the most. One other thing to note is that generally all of these will also have a second function that ends with underscore all, where that means you want to get every single one that matches, and without it, it's just the first match often. But we'll see this in an example. So the first one I like to use is the string detect. So again, we'll just start with a simple example where we create a vector with apple, banana, and pear, and then we use string detect, and now we can see that the output returns true, false, true. And that happens because apple has an E and so does pear. And in this case, we're just searching for the simple character E. Next up, we will look at the words vector. Now that comes built in with the string R library. It's a list of 980 words. We can take a look at the first 6 values. And now, for example, using again string detect, what we'll do is if we run this, we'll see we get 980 trues and falses back. What this is doing is, as you can guess from our previous work with regex, is we are looking for the words that end with a vowel. So in this case, we can use then the mean function to see the percentage of words that end with a vowel. Now, another thing we could do here then is subset using this, and I'll just use the first 5 in this case. So now we can see A, able, absolute, those all end in vowels. Similarly, we can use the exclamation point along with string detect to find the opposite. So string detect, again, in this case, we're looking for words with at least one vowel. But then what we can do is say negate that. So every true becomes false and every false becomes true. And that will give us all the words with no vowels. And again, of course, we can use regex to do that. But the idea here is that sometimes it's much simpler to just use negation of the entire vector rather than dealing with all of the different regex rules. The next common function we want to look at is the string subset function. Now above, we had previously used string detect and then the index to pick out words that ended in a vowel. Again, it was like this. Now, a nice function shortcut is just string subset. So what we can do is, let's just run this simply without any other options, and we'll do this again, and we'll throw on the first 5 just to make it easy. There we go. Now we get the same exact results, and if we look at the string subset help, we can actually see that it's a wrapper around X, string detect X pattern. So it's literally just this kind of work in a nice function, a little bit simpler to write and easier to read. And then it also provides the nice option negate, which again does the same thing we did above, where instead it will return the non-matching option. So let's throw in the same exact search, and this time we'll run it with negate. And now all of the words returned end in consonants instead of vowels. Okay, next up we will look at the string count. This function just counts the number of matches that we get in a string. So now let's look at that same apple banana pear vector from before, and we'll run string count, counting the number of matches for A. So we get 1, 3, 1, which again makes perfect sense because we have 1A, then 3 A's, and again 1A. Now, next up is the extract matches. So this is the extract all function. And what this returns is each match from each string. So in this case, we're looking for matches for AN. We have none in the first string, apple pie. Then we get 1 and 2 and 3 AN in the second string, and then 1 in the third. And that returns the below. Now, I previously mentioned that not all, or that all of these functions also have a version without all. Now, what we can do, we use that in this case, we see some different behavior. It still returns something for each string, but what it does is it only returns the first match in each string within the vector. So again, there's nothing in A, or in the first apple pie. There are 3 ANs in banana candy, but it only returns the first match. And there's only 1 in pear candy, so it returns that. Now, the default return for extract all is a list where each component corresponds to the number of strings in the vector that we provided, and we can use the simplify true, which returns it in a matrix. So the dimensions will be, first, the number of rows will be how many strings there are in the vector we provide, and then the number of columns will correspond to the most matches. So in this case, we had a match of 3 ANs in the second word, so we get a 3 by 3 matrix. Now we can also do some grouped matching. So let's look at how this works. We will use some simple logic to define what a noun is. Now this comes straight from R for data science. Let's search for their explanation here. As a heuristic, we'll look for any word that comes after a or the. That's their definition for nouns. It's just a simple way to illustrate the issue. Now let's take a look at sentences. Again, that is a built-in string vector from string R, where each element is a sentence. In this case, we're looking at the first one. So now, again, we use a nested or within parentheses. So we say, look for a or the, then a space, then any character that's not a space. So that gives us any letter essentially, or number. That goes within the brackets. And then we say plus, indicating any number of matches. Now let's see how that works. So again, the sentence is the birch canoe slid on the smooth planks. Okay, and we run this and it matches the smooth. So obviously in this case, smooth is an adjective, but we're using a simple heuristic. Now we could also break this down into components to see how this works. So when we're extracting, we see that we get a, the, or a, as we would expect. And then we get each non-space word, which includes all of these. And then when we combine them, as we saw before, we get this. Next function we want to look at is string replace. This one replaces the matches with new strings. Again, these are all super useful. So in this case, the syntax, as usual, goes the input, the pattern to match, and then the replacement. So let's go back to our apple, pear, banana example, and we'll replace any vowels with a dash. And again, in this case, since we did replace and not replace all, it only replaces the first vowel. We use the all version of this. Now we can see that the function replaces all of the vowels with dashes. There's a lot of extra flexibility that we can do with string replace. So now let's use this vector here. 1 house, 2 cars, 3 people. And what we can do is use a named vector for what we want to replace. So let's watch that. So now what happens is the name, so in this case, 1, we're saying replace 1 with the word 1, number 2 with the word 2, and so on. So then we can see with the output, all of the numbers that we've named here in this named vector. If you look at the output, we've replaced this character with this word, this character, this word, and so on. So this string replace all function is very flexible. As usual, the string R library is designed to be flexible and easy to use, and we can really see that with this function. Now, something else we can do is replace with back references, if you recall working with back references previously. So now let's again look at sentence 1, and let's see what happens when we use this string extract. So what we're doing here is saying the first match, that's not a space of any amount. So then a space, then birch, then canoe. And what we can do now with the back references is say, let's replace things in a different order. Now let's look what happens here. Now it becomes the canoe birch. The reason why is because this first match, which happens to be the word the, that's our first match. That stays in place. The second match is the word birch. We have that placed after the third match. So what we've done is we've switched the third and second matches with each other. And now that's why we get that different order in the sentence. Pretty cool. Next up is the string split function. Now we can split a string into a vector based on the matches. So again, we'll use sentence 1, and we'll run string split. In this case, using the space as the splitting object. And what we get is a list object. And then the first element in that list is a string. Or is a string vector, pardon me. Now, if we do that, for example, we can simplify it ourselves, and we see that we get this string vector. Again, as usual, there is a nice, simple simplify option, which turns the output into a matrix instead of a list. And finally, there's also the option n equals 2, which says only return a vector of 2. So what that means is we can only have 2 separate strings in our new vector. So it only splits on that first word, and then the rest is returned as is, as one long string. Now there are also a few different modifiers that we can use. And what we want to do there is we can look up the help for boundary, our first example. We see they come in the modifiers help page. There's 4 here. And in this case, we're looking at boundary, which is defined as matching boundaries between strings. And then we get the different types that we have to use. So in this case, we have a string. This is a sentence, period. This is another sentence. So now let's see what happens when we use string splits. on the boundary word. And as you can see, it behaves as expected. We get all the words back. So in this case, boundary has some built-in rules for what different things mean. We will skip the locate just for 1 second and take a look at a few of these other options. So regex doesn't usually need to be used because that is the assumed behavior. So for example, when we're doing string view, we only get the first one. Saying regex around a IOU is the same thing as just running it regularly because it assumes regex. Now we get a little bit different behavior when we use the fixed option. So in this case, fixed means to actually search for that exact string. So this is just another way to kind of escape from regex. Using fixed says actually just search for that exact string rather than using the regex rules. So that's why in this case, we're actually searching for this AEIOU string and it matches the complete string. The reason you might want to use regex is because you can also give it other options. So in this case, we can look at the help again as usual. There's ignore case, multi-line, that kind of thing. So let's look at the bananas string. We can see that only banana is returned because the others have a capital B or all capitals. However, what we can do is use a nice ignore case option, and now it returns all of them because it ignores upper lowercase and just searches for the letters. The regex function also gives us the option to work with multi-line strings. Now, by multi-line strings, I have an example here where I actually have a new line within them. So when I print that out, for example, we actually see that new line special character is within the string. Now, normally that will affect the behavior. So if we search for the strings that start with line, we only get one. Now that makes sense because it's treating this all as one string. So we just get this line back. Now what we can do is use multi-line. If we read the documentation here, it says if true, $ and caret match the beginning and end of each line. If false, the default only match the start and end of the input. So by using multi-line true, we can treat each one of these as its own string. Now let's do that. And what we get is line, line, line. So we get all three of these returned. And another nice thing from the regex function is the comments option. So what that allows you to do is write this nice multi-line regex pattern, and then you can add in comments using the usual £, and it will ignore all of these past that as usual comments are. So we can just look at an example here. We create some rules from searching for a phone number, and this example is straight from R for data science, and then we run it, and as you can see, we get the match below. One last function we can look at is the string locate function. Now what that does gives you the start and end index for a match. So for example, let's search for the word birch. Now if we walk through it, start counting the characters, 1, 2, 3, spaces 4, 5 is that B. We see that it's where our start is, and then continue counting. 6, 7, 8, 9, that's where the end is. So that returns the start and end index of our match. As usual, we can use that with regex. So in this case, we search for vowels. It returns the first one, which is the E and the. And of course, we can use the locate all version, which returns this list. And in that list is a matrix with start and end for each match. Next up are the exercises. So the first one is using X equals the string written there. Write functions to 1, extract all individual number characters, 2, extract whole numbers, and 3, extract 10K. Second exercise is write a function to extract the exact string written here when anywhere in a string or only the entire string. 3, we'll use regex to match a string that contains Q that is not followed by a U, such as QI. Then match all words using the built-in words vector that end with 3 or more consonants. And finally, describe in words what these expressions will match. Now go ahead and pause, work on these, and return to the video when you're ready. Okay, let's take a look at the solutions. So for the first one, we want to extract a few different values from this string here. So let's define X there as usual. Now the first one is extract all individual number characters. Nice simple solution where we just use the double backslash and then D. We get that in return. Second solution, or second problem, is extract all of the whole numbers. So now we have to think about what we've learned and combine them. So again, we start with the digits indicator. Now we wrap those in the square brackets. And then we use the repetition plus sign. So what we say is all grouped digits of any length. And now, as you can see, we get 122 and 10. Now, lastly, we want to extract just 10K. So again, we start from the previous solution where we say all of the numbers of any length, but now we just throw in this extra K, and as expected, we get 10K back. Number 2 is write a function to extract this exact string. So the complication here is that these are all special characters, so you have to think about how you want to work through that. So now we'll use this string here as our example. So the first one is just the exact string. Second one is again the search string, but with some letters wrapped around it. So now this one isn't too hard, it's just messy to write. All we have to do is use our escape backslashes, the double for each character. In this case, as expected, we get a match in both strings. Now, the second one was when it's only the entire string. So all we have to do is throw on the caret at the start, because that says string starting with, and then the $sign ending with. So we run that, and now we only get the first value. Okay. Now numbers 3 and 4. Number 3 was write a regex to match a string that contains Q that is not followed by U. So we'll use a small example here with quit and QI. So in this case, we want the letter Q, and we say wildcard, but it can't be the letter U. So again, in this case, we get QI back, but not quit. Now, finally, number 4, match all words that end with 3 or more consonants. So we think back to the curly brackets for repetition, where we use 3 as the minimum and a space indicates any maximum or any amount for the maximum. We combine that with what we've seen many times now, where we negate A, I, or U. And then finally, we throw on the $sign to say ends with. Now let's run that, and we get this list of words back. Now the final question is describe in words what these expressions will match. So parentheses, dot, 1, 1. The second one is double parentheses, or double parentheses, dot, and then 2, 1. So now immediately we start thinking back to the back references. So let's take a look at the solution. So this one is the same character appearing 3 times in a row. So the reason why is because first we get any character using the dot. We wrap that in parentheses to indicate a group. Then we say we want to get that first match again and that first match another time. So in total, it's 1, 2, 3 of the exact same character. So in this case, for example, AAA would match that string. Now, in this case, it's a similar idea, but a little bit more complicated. So again, we're saying any characters. In this case, it's a pair of characters, but the second one has to repeat, and then the first one. So what that is a pair of characters followed by the same pair of characters, but in reversed order. So this one here corresponds to this match. This one here corresponds to that match. So in that case, an example here would be A, B, B, A. Because again, A, that gets mapped to the first group. Then B is the second. Now we say we want to see the second match and then the first match. So 1, 2, 2, and 1. Hopefully these solutions eventually make sense. If they don't make sense now, again, it's the type of thing where regex really just needs practice and use. And with that, we've actually reached the conclusion of our presentation. Quick reminder, strings are the ordered set of characters, such as hello world, and we define them with quotes in R, either single or double. The string R package is a powerful yet user-friendly library for string manipulation. It has almost all the string functions you'll use. And then regex, of course, is confusing, but when it's the right tool for the job, it is extremely powerful. Thank you so much for joining me again, and I hope that my presentation has been helpful for you in your journey of learning R. Have a wonderful rest of the course. Thank you so much.